I will share the quiz today, right? And that will be the high test of hypothesis related, and then we have correlation regression quiz. If you people allow me, it can be conducted tomorrow and otherwise on Friday. So choices with you. जी. What do you suggest, my dear students?
Sir, on Friday.
Yes, sir, make it on Friday. And sir, what about timing? When will you share?
I think after 4 o'clock it will be open. 4 or maybe 5, whatever is convenient to you people.
Sir, what time is decided for today's quiz?
Today's quiz, I think 6 o'clock is okay to everyone.
Yes, sir.
Sir, in group there was issue to someone.
सर जवेरिया और आयजा कह रहे थे कि वो 8 तक फ्री नहीं है.
हाँ, exactly, sir.
कब तक फ्री नहीं है?
वो कह रही थी कि 2 से 5 कर लेना, 8 नहीं.
अच्छा 2 से
After 2.
ठीक है. 4 o'clock is 4 o'clock is suitable to everyone.
Yes, sir.
Okay. Last time we were discussing about this multiple linear regression analysis. Sorry, and just I'm going to wind up this because on the one side this is the topic just like the last topic of your course at this point of time, and 1 or 2 topic was there, but they were placed with the option that if we have the time then we can do those topics. Anyhow, due to this to an extent pandemic, we have some disturbances, so flow is going to be disturbed. So I'm just going to complete only up to the multiple linear regression, right? So one thing is clear, I hope in your mind, that this multiple linear regression is actually related to the variety of variables which are playing the role of independent variable, and one variable is dependent variable, and that is your choice. Mean to say, based on your theory or whatever assumptions you may have, accordingly you can fix a specific variable as a dependent variable and keep other variables as an independent variable. Now the point is that whenever we are going to estimate these models, we are going to face the problem of residual. Residual mean our actual value may deviate from the estimate value may deviate from the actual value. So we have y hat, which is estimated value, and we have y, which is the actual value. The difference between two is basically showing the error term, the residual. Right? So this residual should be minimized. So our purpose for applying all these techniques are just to minimize this error. Right? Second important thing is related to the homoskedasticity or heteroskedasticity. Homoskedasticity is not a problem, but heteroskedasticity is the problem. Actually, what it shows that the variance should be same across different values. Now, therefore, if it is going to vary, the variance is going to vary, then it is going to create problem of heteroskedasticity, right? So I'm just going to draw this diagram and show this. The residual should follow the normal distribution. So that is the thing I have already mentioned. Whenever you estimate your model and residual values are separate without any trend, then this condition is going to be fulfilled, normal distribution, right? And successfully values or successive values of the dependent variable must be uncorrelated because it should not have any kind of correlation with each other. Now, every next value of y, whatever you are going to estimate through the model, they should not depend upon the previous value. Otherwise, you know that autocorrelation or such kind of phenomena, maybe their problems are there. So just like I may draw the diagram to show you. Right. Let's suppose this is your trend line, and these are the data points which are moving away. Let's suppose if your variance is remains same, right? Let's suppose if I'm going to draw a line along with this, should be same across the line. Both difference between two lines, both blue lines should be have the same deviation from the original this line of fit. So line of fit is actually, this is your line of fit y head. So if this deviation across values is going to be have same, it's not going to vary a lot, then there is no heteroskedasticity, then homoskedasticity exists. That is the basic condition. It should be. But if that, let's suppose your data values are this, in that case, you know that let's suppose your lines are passing through this. So it should be straight line. Flip over the mouse is below. So let's suppose, so if it all values lies within this range or lies within this range, then homoskedasticity exists. But just like these values are not lying with, so deviation is going to change. So this shows the heteroskedasticity problem, right? So variance is going to change. Variance is not going to be same across different values, right? Of y, of y against any given value of x. Okay, second thing is the ANOVA table. ANOVA table actually gives you, purpose of ANOVA table is to find out the residual sum of square, RSS, and residual sum of square and regression sum of square, right? So usually regression sum of square and error sum of square, ESS. And they are going to be divided with each other to give you the F statistics. Last time I have give you that how you can calculate without generating this ANOVA table. So this RSS shows actually the explained variation, residual, regression sum of square, regression sum of square shows what? The explained variation, how much variation in the model has been explained, how much variation in Y has been explained by this model, right? And remaining variation which is not explained is called unexplained variation or random variation, and that is referred to error sum of square. In some cases they are known as residual sum of square. You can also use, but just avoiding the same word, so I just use error sum of square. Otherwise same, errors and residuals are same. So this point is clear. We are going to actually show how this value is going to be calculated. Last time I have done this. I'm just going to share this sheet with you that, sorry. Example. Last time we have calculated this F statistics, and we use this regression sum of square and this error sum of square. So this is residual sum of square, this one. So if I may make it red, and this one is explained sum of square. I will make it green and bold, right? So these two values are important. We take the ratio of both values and we get this F statistics. And we need to compare, this F statistics with T value, mean to say we want to know that whether it's a significant values or not. So what is the TF tabulated? F tabulated F tab, right? F tabulated, and you can generate this F tabulated value by using this F function F inverse, right? F distribution. You can observe X degree of freedom, X freedom, and cumulative. That will give you the distribution. We don't need distribution. We just need this. Return the inverse of the left-tailed F probability distribution, right? So we are going to use this F inverse, right? Just like we have calculated T value through T inverse. So we are going to measure F value F inverse. So at 95%, sorry, a 95% probability, right? Mean confidence interval is 95% or 5% degree of freedom. If degree of freedom is 10%, then it will become 90%. If degree of freedom is 1%, then it will become 99%, right? So choice is your, accordingly you can. Secondly, you know degree of freedom. How you can calculate degree of freedom? Already it is mentioned, degree of freedom is here. 16 is the degree of freedom. So you can observe by yourself. It is given here, or you can click this to show that you can take this value as it is here, right? Or otherwise simply you can take the value, just typing it, degree of freedom, and then you go for degree of freedom 2. This is what first degree of freedom. There are two things which need to be noted down. One is n minus k, and the other is k minus 1. First degree of freedom is k minus 1, and second degree of first degree of freedom is n minus k, and the second degree of freedom is k minus 1. K minus mean how many variables? 1, 2, 3, 4. 4 minus 1. 4 minus 1 is 3, right? So you will go for this. We have used 3 variables now in this equation. 1, 2, 3, 4 variables. 4 variables, and then minus 1 is 3. So we close this and we enter this. This will be the F tabulated value, right? This is the table value of, and it will tell you that whether the F stat is significant or not. How you will make the decision? If F stat is greater than F tabulated, you will reject H naught, right? So if let's suppose I'm going to write here, reject. What is H naught in this case? H naught, if F stat is greater than F tab. Clear? In this case, it is not, therefore you cannot reject H naught. And H, if you cannot reject H naught, what it means? It means overall this model, because F shows beta 1, beta 2, beta 3, all are equal to 0, beta naught, right? One of them may be, if we reject H naught, what is H naught? I may mention to you for your convenience. H naught is beta naught equal to beta 1 equal to beta 2 and equal to beta 3. So A is used here, so I'm just going to make it it's beta 1, because we are not using beta naught now anywhere. Beta 1 is equal to beta 2 is equal to beta 3 or B3. Both are equal, all three are equal to 0. So this is the H naught. If we reject H naught, it means they are insignificant. If we do not reject, so if we do not reject H naught, it means they are insignificant. If we are capable to reject H naught, it means they are significant. Beta 1, beta 2, beta 3 are significant. These variables are affecting the dependent variable. What happens in this case? We are unable to reject, because you know that one of the variable, whenever we have calculated last time, this variable shows that it's not showing the significance. So one of the variable, if not significant, sometimes your F value is not significant, because you need to revise your variable. So whenever these statistics are significant, let's suppose in this case 2 variables, beta 1 and beta 2, they are significant, their T values are significant. So it means both are important variables. And just last time we have calculated this one, so I'm just going to mention this one with lag values now, 2 and beta 1, and intercept can be used as beta naught. Both option is there, or you can use A. There's no difference between. Yeah. The point is that let's suppose these 2 variables are significant, let's suppose I'm just going to show this green, right? They are significant, but this one is not significant. And this one is not significant, therefore I mentioned it with different color. It means if you are going to use this strategy, the beta 1 is equal to beta 2 is equal to beta 3, mean all three are equal to 0, and you want to reject them, because of this variable you cannot reject this hypothesis. If it is close to significance, you may reject H no, mean value of F stat may increase and it will come to 9, 10, or it may be 8.7, 8, 9 in this way, right? In that case, marginally you can reject that. But as you know, this value is so much low, T stat is so much low that it's never be a significant or close to be a significant. But they are very clear cut significant, right? Because here I just give you the T stats, T tabulated value as well for your convenience, so that you can compare all these T stat, and this can be calculated by T inverse. Here you need 0.95% probability, and degree of freedom is 16. Here you will, I think, use probability with reference to this one, huh? You will use this level of significance, right, for probability. Let's suppose I may check this one here as well. 0.05. No, it's too low. It's not, because it's not in fraction. So it is 95% confidence interval. Anyhow, this value is 2. So clearly 2.4 and 4.8 are greater than this value. Therefore, straightforward, you can reject H naught in case of beta 1, beta 2, but you cannot in case of beta 3. So this is the problem. So in that situation, F stat may be lower, it is not significant. So you can clearly mention that F stat is not significant. So you have to revise your variables, and then you can find out. And usually it shows this kind of situation that residual sum square and error sum square, there are whenever you are taking their ratio, that ratio is giving you the idea that the overall variables, whatever you have used in the model, they are not jointly playing vital role. Some of the variables may be not effective variables, some of the variables may be irrelevant, some are just creating extra burden over the model, so you need to eliminate them. You can observe this situation quickly just by doing the same calculation on the basis of without including this variable. Let's suppose if I'm just going to do this quickly here. Oh, sorry, not cut. I'm just going to copy here. Here. And then 1, 2, 3 variables I'm going to choose. So I'm just going to copy this here. Right? And just I'm going to use the equation, the formula same, only taking the beta 1 and beta 2, right? I'm not going to take this third variable, and third variable you already know is what? This Fernand's age, right? So this Fernand's age is not going to play any important role at this point of time. So first I'm going to delete this, right? The Fernand's age is not going to be taken here, right? And all these values are I'm going to take in form of log. So this heating cost, these are the in form of logs, right? So I'm not going to pick which variable, this one, right? So just like I'm going to color this, I'm not going to pick this variable. Otherwise, I'm going to pick these 3 variables, right? And then going calculating this value equal line estimation, and then go for X value. Sorry, first Y values. This heating cost is the Y value, right? Comma, and then I just pick these two variables. Then comma 1, close. I don't know who will get. Oh, good. We get all the answers. So the whole area is not selected, even though. But if you click Shift Control Shift Control Shift and Enter, then you will get the answers. So what happens here? If you just observe the t statistics quickly, we can calculate this t statistics slope divided by your error estimation, and then you are going to apply for all these three. The t value already calculated previously. We have this t value, this one t value 2.1111, right? So it is t stat. So t stat is not t stat, it's t tab. So make it correct. T tabulated. T tab, right? And here it's also t tab. And equal to t inverse, you will get this probability 0.05, comma, and degree of freedom 16, and then you will get this answer. So now you can observe these values are again, because only one variable is excluded. Now we'll get the F statistic, because this is important. Now what is F? Has been improved. F stat, and F stat is equal to your regression sum of square divided by your residual sum of square, and it comes only 1.85. It's too low because variables reduce there. Anyhow, what will be the outcome? And then the F tabulated regression sum of square. Previously we have calculated regression sum of square here for this 0.9 and this. Okay, values are correct. And F tab is sorry, F stats is, we have calculated this 3 and 9.95. I think I have to check it out, because probably this will be the 0.5 value, right? If it is 0.5%, then we'll get this one, and this shows this significant. Same thing applies, because 8 is too much high. Usually it is not coming in this way. So this is basically the same. So here also we are rejecting H naught. So F stat is greater than F tabulated. Here we also reject this. So here again we are going to reject this, because F stat is, F tab is 0.308, right? So in this way you can calculate and you can verify that whatever ANOVA table which is giving you these values, basically how it is going to reflect that whether your model is effective or not, right? So you got this through even by using Excel sheet or any other kind of program. But in Excel sheet we can use only two variables for that purpose in this table form if we want to have the result. And so otherwise other method is already I'm using. So coefficient of multiple determination R square, it's already, it is symbolic by capital R square, range 0 to 1, cannot be assumed negative value, and so you can calculate the sum of square as over total sum of square. As you can calculate this coefficient of determination R. This is sum of square regression, right, divided by total sum of square. So usually whenever you are going to apply these softwares, then directly you can get this value just like we have calculated previously. But in this case, whenever we are applying this line estimation technique, we don't have the total sum regression. sum square, but we can take the summation of both. So let's suppose R square can be calculated here. In both model, let's suppose here the space is there. So R square QR, it is equal to your residual sum of square divided by sum of these two values, this one plus this one, close, enter. So it shows the 65% variation is being explained, right? So you can calculate. So in this situation, you have to calculate things by yourself whenever, if you are going to apply the software directly, you can get all these results. So what is our square here? Equal to, just like this, divided by this one plus this one, same values are same. Marginally it is a bit larger, higher, and it is smaller. And you should know that actually whenever you are increasing your variables, R square is going to increase slightly, right? So 6.6517 to 0.6527, right? It increased marginally. So in this way, you can calculate 65% of the variation has been explained by this model. So it is already mentioned the independent variables, the number of independent variables in a multiple regression of coefficient, whenever they are going to increase, they are leading towards larger coefficient of determination. So it never be equal to 1. So keep this mind, because sometimes you will get 0.98, 0.99, very close to 1, na? This R square value. So you can apply any package, software package, and you can get the results directly, right? So all these calculations and all these formulas are actually helping you to identify that. Now correlation matrix is used to show all the possible simple correlation coefficient variable, right? And that is quite useful because in that case you can create some kind of relationship across different variables, right? So correlation matrix mean different 4 variables on the right hand, 4 variables same on the left hand, and cross correlation is going to be compared with each other. Okay, this is the same F statistics we have discussed already, this part. So this show k and n minus k minus 1. So you can use this because depending upon different tables, first you will use alpha state, it is 0.05, 0.05 whenever you are calculating f value. Then you can use k is the 4 variables, you are using a 5 variable, 4 variables you are using, right? And then n minus k minus 1, it is total values are 20 minus 4 minus 1, then it will become 15. So 0.54 and 15, what response you will get, you can incorporate here and you can get that, right? For f stat, f tabulated value, right? Just like here, f tabulated value I have calculated this one, and it is showing 4 and then 15, and then you will get this one. If we are going to apply this 95% confidence interval, this is right. This values it is making sense because basically it should be close to this value. So this is the right thing. You have to use this one. Now it is 3 point something. So just like you can use this value equal and then F inverse, and you can take 0.95 comma 4 comma 15, bracket close, and you will get this. Sorry, 0.5. And this is showing insignificant, right? In this case, this is showing, but in this case, it is showing significant because variables are larger. And in this case, maybe some kind of problem exists because I get the same result here and I get the same result after taking the logs, and therefore there is no difference between two, right? But it is without taking log, so it's quite large value which you will get. And we are taking F stat by taking the ratio of two values, and same we have applied, but definitely it's stat. It's okay. Formula is same, correct? Okay, time is 7 minutes left. Anyhow, I'm just going to move ahead. Basic thing is going to be clear. You have to apply this F table, and you can find the area in which you are going to focus, right? Which area value is going to lie in this rejection region, or it is going to lie in the acceptance region, right? Then you will go for whatsoever F value you will get applying this formula, you will get through this. So one of my suggestion is that you should not worry about the value for this Excel sheet, which is being generated by Excel sheet. I hope that whenever you are going to apply this data set on some software, then you will get more clear cut and the high value of F. Even after taking log, I'm just going to show it through the eViews. Probably you will get some result, and I will show you that what is the result in that case. Okay, for every coefficient you will get this. So actually this test of hypothesis is going to be applied for every value. So it shows that you are going to compare your whatever selected coefficient, whether it's equal to 0 or not, right? So beta I minus 0, or it is straightforward beta divided by standard error, you will get that tabulated t value, whatever I have already mentioned to you. So you are going to make your decision on the basis of that. If two side or the two tail test, then you have to calculate on for both plus minus values, and then you can identify whether your value is lying in. But if you have only one tail test, then situation is different. It's very simple because only one value greater than or less than is desired. Usually it happens when it is equal sign and not equal sign in case of your test of hypothesis, then you have two tail test situation. So whatever results you are getting through softwares, they are giving you the complete idea about, mean to say you may not apply even the tabulated values, automatically probability values given to you, and you can make your decision on the basis of that. So all these can be done by, this is done by the Minitab, but you can also use SPSS. I have mentioned that if you have this opportunity, since we don't have so much time, otherwise I must suggest you to use that SPSS. So this is why, because this short of time, I just skip that component. Otherwise, we can do some practice on SPSS. These are the assumption of the multiple linear regression. Just like the simple linear regression, it shows the linear relationship variation. The residual is the same for both large and small values of estimated y. Right? I mean, this variation are showing the it is not basically there is no heteroskedasticity. This is showing homoskedasticity is well situation. The residual follows the normal probability distribution mean, just like they are going to be mentioned. Again, I'm going to show you because again and again they are coming. So residuals are basically spreaded. They are not showing any kind of trend, right? So, but whenever we are going to show the distribution, taking the mean of this data set, right, and observe the deviation and distribution, So this is showing the normal distribution, right? So data along the mean, this mean value, whatever mean value this residual error has, all the values are lying 50% right and 50% left. This applies that, right? So it's just going to draw the U shape, inverted U shape, so same distribution. So that is basically the normal distribution. The independent variable should not be correlated. This is important because let's suppose if you have y and you have x1, x2, x3, just like alpha naught first constant, and then you have beta 1, x1, then beta 2, x2, right? So they are showing that these variables should not be interdependent. They should not have any kind of relationship with each other. Otherwise, their relationship will affect the relationship, their overall individual relationship with y. Secondly, residuals are independent. Residuals are, these are the residuals. Whenever you are getting residuals, these are the residuals, right? Residuals are getting over the, for every value you are getting residual. This is the residual, one residual. So I just want to make it red. These are the residual. This is the residual. So these are the residuals. Deviation from the actual value, deviation of actual value from the mean value. So these are not interconnected with each other. If they are interconnected, then there is the problem, right? So basically all these assumptions shows that if these assumptions are going to be followed, then your results are correct, and whatever estimation you are going to make through these results are valid. But if there is some assumption violated, then first of all you have to correct that assumption and remove the problem. These are shows the scatter plot. Right. These are the residual plot. In this case, you will observe the relationship is showing some kind of connectivity, some kind of behavior, right? But it is not showing any kind of behavior. Then these are the normal probability. Values should lie very close to this line. A histogram shows, histogram sometimes not showing so much clear-cut picture. Then we have these problems if we are going to have assumptions are not going to be followed. Which assumption is not going to be followed in case of multicollinearity? Less than 1 minute is left, so you may rejoin to wind up, right? I will not record that component, that part, but we may discuss about it. Basically, major things are clear. I'm just going to discuss about these, or we may record that component even. Don't worry. So please, what is the multicollinearity? This is the relationship between two variables, just like I have mentioned in previous slide. This slide, variables are interconnected, just like here. X1 and X2, they are interconnected. If that kind of problem exists, then multicollinearity will exist. Just like in case of